Here we are back, exponents and radicals, lesson 3, entire radicals versus mixed radicals and mixed radicals, part 1. I guess they break it up into 2 parts because there's so much to know. So from last lesson, the product or quotient of the roots of two numbers is equal to the root of the product or quotient of the two numbers itself. So that was this rule. Square root of 2 times the square root of 3 is also equal to the square root of 6, or division as well. Square root of 2 over 3 is equal to the square root of 2 over the square root of 3. And you can work those backwards and forwards, one way and the other way. Okay? The sum or difference, so addition and subtraction, we cannot do. So we're not even looking at that right now. Okay? So we're just looking at multiplication and division. And here's our restatement of our rules. Today, we're going to look at, well, how can we simplify these radicals? So we're going to work them backwards most of the time. So in this lesson, we use the above rules in reverse. Okay, so working backwards. Example 1, write the following as a product or quotient of radicals. Square root of 24 is also the square root of 4 times 6, which is also the square root of 4 times the square root of 6. Now, we know that the square root of 4 is equal to 2. So this could also be written as 2 root 6, or 2 times the square root of 6, but we never write that multiplication symbol in there. Okay. If we look at the square root of 18, the square root of 18 is 9 times 2. So that's, not 9 times 2, which could also be written as the square root of 9 times the square root of 2. And the square root of 9 we know is 3. So this could be 3 times the square root of 2. And then more simply written, 3 square root 2. So basically what you're trying to do when you're writing a mixed radical is look for the perfect squares or the perfect cubes or whatever root you're trying to deal with and pull those out to simplify. There's another way using prime factorization, which I will show you in a moment. Okay. So let's look at the square root of 11 divided by the square root of 4. So this is also the same as the square root of 11 over the square root of 4. And I know that the square root of 4 is 2. So this is the square root of 11 all over 2. Another way to write that. Now, another way to determine what the mixed radical is, because sometimes maybe these numbers are so big, you can't see what the perfect squares are within those numbers. So another way is to use prime factorization. Okay, so I'll do the square root of 18 using prime factorization. I'll even switch colors just to make it easier, a bit easier to follow. So what I need to do is break 18 down into prime factors. So I do my factor tree. This is going to be 2 times 9, and this is going to be 3 times 3. So I know that the square root of 18 is also 2 times 3 times 3. And because this is square root, remember there's a little 2 out here we never write, that little 2 out here we never write. Because this is square root, I look for groups of 2. There's a group of 2. There's a pair. That is going to give me a 3 on the outside of my radical sign. There's nothing left over. That's it. Done. Okay. I could also do 24 the same way. Square root of 24 is 2 times 12, which is 2 times 6, which is 2 times 3. So I know that the square root of 24 is 2 times 2 times 2 times 3. Well, there's only one pair. There's that pair. That's going to give me a 2 outside the radical sign. What am I left inside the radical sign? 2 times 3. Well, 2 times 3 is 6. 2 root 6. We get to exactly the same place. Okay, so that's using prime factorization, which eventually you'll probably have to do because some of the numbers you might not see what those perfect squares are. Okay. Entire radicals and mixed radicals. Use a calculator to approximate the value of each radical to the nearest 5 decimal places. So when you punch these into your handy dandy calculator, you get 8.94427. Here you get 8.94427, 2 root 20, square root 80, 4 square root 5, 8.94427. And you can see that all of these are the same, right? So a mixed radical, okay? Square root of 80 is a whole radical or an entire radical. A mixed radical contains a coefficient and a radical. Mixed radical contains a coefficient and a radical, okay? Each of these entire radicals and mixed radicals all equal the same numerically in a calculator, which means they're all equal, right? So it's just a different way to write these values. Kind of like if you think about 2 over 4 is equal to 1 over 2 is equal to 0.5. Those are all equivalent methods or ways to write that same set of numbers, okay? Same with mixed radicals. Complete the following to explain why the three radicals are equivalent. Well, square root 80 is 4 times 20, which is square root of 4. Whoops, where's my pen? Which is square root of 4 times the square root of 20, which is 2 root 20. So I can simplify that. Square root of 80 is also 16 times 5, which is the square root of 16 times the square root of 5, which is 4 square root 5. Square root 80 is an example of an entire radical. The number is entirely under the root symbol. 2 root 20 and 4 root 5 are both examples of mixed radicals. So those are both examples of mixed radicals for the square root of 80. But one of them is more correct than the other. And again, that goes right back to this whole scenario. 3 over 6, 2 over 4, 1 over 2. Those are all equivalent, but only one of them is more correct. As a final answer, 1 over 2. This is the most reduced, the most simplified form of those numbers. So this is the appropriate one to write as a final answer. Same with mixed radicals. If I can simplify a radical further, then that is your final answer. Okay, you want them as simple as you can possibly make them. Let's go over the page 16 now. So entire or pure radicals, they can be expressed in this form with some kind of index, some kind of radicand, no coefficients outside. So for example, square root 20, square root 80, cube root 17. Mixed radicals will have a coefficient out in front. 2/3 square root 5, 8 square root 7, -9 cube root 17. Those are all mixed radicals. Okay, so entire radicals only contain the radicand as the number and of course the index on the root. Every mixed radical can be expressed as an entire radical. So I could make these into an entire radical following a particular process. Okay. To determine if an entire radical with an index of 2 can be expressed as a mixed radical, we need to check if the number has a factor, which is a perfect square. So again, there's two ways to do it. You can look for those perfect squares or perfect cubes. I think it goes into perfect cubes. Or you can do your prime factorization tree. And I'll do some of these both ways, just so we can see them. So let's look at this example here. Complete the following to convert square root of 108 into a mixed radical. So the entire radical is 108. 108 is something times 3. What's that something? That something is 36. So when I split this up, because I can, following my rule, this is square root of 36 times the square root of 3. And I know that the square root of 36 is 6. So this can be simplified into 6 square root 3. Or, and I'll show you the prime factorization right here, right now, because I think I got lots of space to do that. Square root of 108. I know that divides by 2, so that's 2 and 54. That also divides 2, and that's 27. And that's going to be 3 and 9 and 3 and 3. So the square root of 108 is also the square root of 2 times 2 times 3 times 3 times 3. Because this is square root, I look for groups of 2. There's a group of 2, and there's a group of 2. Each of those groups of 2 will give me one of those numbers, 2, and then times 3 outside the radical sign. And I'm left over with this lonely 3, square root 3. And then I just simplify. 2 times 3, 6 square root 3. So now you can see how it works with prime factorization as well. I have different students, different methods. These are both legit methods. You can choose one or the other. The difficulty with prime factorization is sometimes it takes a little bit longer, okay? But it's pretty easy to divide by prime numbers. Here, I have to know what my perfect squares are. And when I get into cube roots, I have to know what my perfect cubes are. When I get into fourths and fifths roots, well, that gets really complicated because now I need to know my fourth and fifth roots, right? So they both have pros and cons. This is just stating, this is just kind of saying, well, you may have to do an extra step. If the perfect square, which is factored out, is not the highest perfect square, then the process will require more than one step. So if you happen to choose something that's not the highest, then you'd have to do it all over again, okay? Because this number, the radicand, won't be small enough. Okay? Convert the following entire radicals into mixed radicals in simplest form. Square root 50. I'll do it both ways. I'll do 50 both ways. Square root 50 is the square root of 25 times 2. Well, I know that the square root of 25 times the square root of 2 is the same thing, and the square root of 25 is 5, so 5 square root 2. Using prime factorization, I'm going to split my 50. It's going to be 2 times 25, which is going to be 5 times 5. So I know that the square root of 50 is 2 times 5 times 5. There's a group of 2. It's going to come out of my radical, and I'm left with that inside my radical, 5 root 2. Same place. Okay. Like I said, different strokes, different folks. It's going to depend on your knowledge and ability to remember all of those perfect squares. 45. 45, square root of 9 times the square root of 5, which is the square root of 9 times the square root of 5. That's a 9, which is 3 square root 5. Yeah, and I'll do, you know what, I'll do 320. It's bigger. I'll do 320 using prime factorization. It's harder to see. With 45, it's easy to see what the perfect square that goes into that is, but the 320, it's a little tougher. So 320. 320. What is going to be a possible number that's going to go into 320? I'm going to tell you, I think it's 64. Square root of 64. 64 times 5 is 320, which is equal to the square root of 64 times the square root of 5, which is equal to 8 square root 5. Now, by prime factorization, maybe I couldn't tell if that was 64. And the bigger the numbers are, the harder it is to see those perfect squares. We did this one because I kind of gave you the hint, right? I knew it was 64 because I did the question previously. But maybe you didn't, and you're stuck trying to figure it out. You'd have to do a lot of trial and error to get there. So I can use prime factorization. Say, well, I know that 320 divides by 2. Dividing 320 by 2 is going to give me 160. 160 by 2 is going to give me 80. 80 by 2 is going to give me 40. 40 by 2 is going to give me 20. 20 by 2 gives me 10. 10 by 2 gives me 5. So 320 is 2 times 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6 2's times 5. Now it's square root, so I look for groups of 2. There's a group of 2. There's a group of 2. There's a group of 2. This is going to give me a 2 outside. This is going to give me a 2 outside. This will give me a 2 outside. And I'm left with my lonely 5 inside. And I multiply all of these together. 2 times 2 times 2 is 8 square root 5. I can get to the exact same place. Okay? Exact same place using prime factorization. Over the page. Over the page, example 3, convert the following radicals to mixed radicals in simplest form. So this is where we're working the other way around. And again, a couple of ways that you could, convert these radicals into mixed radicals. No, we're still doing the same thing. Oh, except we have a coefficient out in front here. So we look at 192, and I know that 192 is 64 times 3. So this is going to be the same as 2 times the square root of 64 times 3, which is 2 times the square root of 64 times the square root of 3, which is 2 times 8. Square root of 64 is 8 times the square root of 3, or 16 square root 3. And again, you can do this by prime factorization. You'd prime factorize the 192, you'd end up with 8 square root 3, and then you'd multiply the 8 by 2. Let's say I'll do 160. I'll do 160 here by, let's say I'll do 160 by prime factorization. Okay, so 160 divides by 2, that gives me 80. Divides by 2 gives me 40. 2 and 20. 2 and 10. 2 and 5. So this is 3 over 4 times the square root of 1, 2, 3, 4, 5, 6, 5 twos. 2, 3, oops. 3, 4, 5, and a 5. Now, this is a group of 2. That's going to give me a 2 out. This is a group of 2. That's going to give me a 2 out. I'm stuck with my 2 and 5 on the inside. And I can't forget my 3 out of 4, 3 over 4 to begin with. And I multiply these 3 coefficients now together. 3 out of 4 times 2 times 2. 3 times 2 is 6. 2 is 12. That's 12 over 4. Straight across the top, straight across the bottom. Square root 2 times 5 is 10. And then 12 over 4 is 3. 3 square root 10. Question C. Square root of 7 divided by the square root of 9. Remember, I can split this. That's the square root of 7 over the square root of 9. I know that the square root of 9 is 3. So this is square root of 7 all over 3. Done. Now let's move on. So now we can also do the same thing when we have an index bigger than 2. Except now, if it's a 3, we need to know all of these perfect cubes. If it's a 4, we need to know all of the 4th root perfect ones. If it's a 5, we need to know all the 5th root perfect ones. So it gets a little tricky. So this is where prime factorization becomes kind of key. So I know that 54 is 27 times 2. Trying to find the cube root of what? 54, sorry. So 54 is 27 times 2. So I can split that up now into the cube root of 27 times the cube root of 2. And I know that the cube root of 27 from my nice handy dandy chart over here is 3. So this is 3 cube root 2. And it's important to have that index on there. Okay? You can't forget that index. If the index is 2, it doesn't need to be there. If it's anything different, it needs to be there. Okay. And that's where it says similar processes involved for indices greater than 3. So if I have an index greater than 3, so it's a 4 or a 5, but prime factorization works much better when we have a bigger index, because otherwise you have to remember what all of those perfect fifths and fourths and sixths are. Okay. So the cube root of 6,000. Oops. Cube root of 6,000 is our example 4a, which I know is the cube root of 1,000 times 6, which is the cube root of 1,000 times the cube root of 6. And the cube root of 1,000 is 10. So this is 10 cube root 6. Now that one's not too bad. It's pretty easy because 1,000's on our chart. We can remember that. But for 320, our chart is cubes. It's not fifth roots. So I would need to know some perfect fifth roots. Well, I know a couple, but I'm pretty sure you might not. And you might be able to figure 1 or 2 off the top of your head fairly quickly. So this is where prime factorization really comes into play. 320 divides by 2 to give me 160. 160 divides by 2 to give me 80. We've done this already, so we know what it is. 2 and 40. 2 and 20. 2 and 10. 2 and 5. So I know that 320 is the same as 2 times 2 times 2 times 2 times 2 times 2 times 5. This is fifth root. Now, because it's fifth root, though, I look for groups of 5. 1, 2, 3, 4, 5. There's my group of 5. That's going to give me a 2 outside my radical. There's no other groups of 5. I'm left with my 2 times 5 inside. Don't forget it's fifth root. So this is 2 fifth root. 2 times 5, 10. Okay. Question C, cube root of negative 16. So the first thing you ask yourself, Is this an odd root of a negative? Yes, it is. So this is doable. If it's an even root of a negative, you cannot do that question. It's not possible. Okay? So this is an odd root, so I can do this. Now, two different modes of thought here. We can either take the negative out, or we can leave the negative on the inside. Either way, your choice. Okay? So if I start to break this down, if I do this by prime factorization, I'm going to say, well, you know what? This is going to be 2 times 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. But if I'm doing it by prime factorization, I should probably show you all the steps, right? That's 8. 8 is 2 and 4. 4 is 2 and 2. Now, how do I deal with the negative? I look at this and I say, well, that's a cube. So I'm going to have 3 negative 1s. Negative 1 times negative 1 times negative 1 times my 4 2s. Then I don't have to worry about my 2s or my other numbers other than 1 being negative. So there's a group of 3. My negative 1 can come out. Here's a group of 3. This 2 is going to come out. I'm left with a 2 on the inside. That's a 3. I multiply these together. Negative 1 times 2 is negative 2. Cube root 2. Or, like I said, you can do this one or two ways. That's with the negative on the outside. If you want to leave the negative inside, then my prime factorization would look like this. My negative 1 all by itself, times 2 times 2 times 2 times 2. Well, there's a group of 3. It comes out. Cube root. What's left over? Negative 1 times 2. Negative 1 times 2 is negative 2. That answer or that answer, perfectly fine for this type of question. Possibilities. Over the page. Extension. Oh, this is an extension activity. Oh, no, you should be able to do these. Okay. Since x cubed times x cubed is equal to x to the 6th, then the square root of x squared should be x cubed. There's 2 groups of x cubed, correct? Also, since the square root of x to the 5th, x to the 5th, x to the 5th all multiplied together gives us x to the 15th, the cube root of x to the 15th should be x to the 5. There's 3 groups of x to the 5. So this is using the process of perfect cubes and squares as opposed to prime factorization, but you can use prime factorization also. Okay. The square root of x to the 4th would be the square root of x squared times x squared. Well, there's 2x squared, so this is going to be x squared. The square root of y to the 10th would be the square root of y to the 5th times y to the 5th. There's 2y to the 5ths. Y to the 10th, oops, that should be a 5. Y to the 5th. Now this is remembering your exponent rules from last year also, right? When I'm multiplying numbers together at the same base or variables together at the same base, I add the exponents together, right? A to the 8th, b to the 6th, square root. So this would be a to the 4th times a to the 4th times b to the 3 times b to the 3. That's a single b. So there's a group of a4, b3. There's a pair of those. So it's a to the 4th, b cubed. Complete the following to convert x to the 5th, square root of x to the 5th to a mixed radical. So again, we need to know the perfect square or cube in it. So x to the 5th is the same as x to the 4th times x, which is the same as the square root of x to the 4th times the square root of x. And square root of x to the 4th, which is the square root of x squared times x squared, would be x squared times square root x. And I'd write that here, x squared square root x. Now, using prime factorization, square root x to the 5th, I would still prime factorize x to the 5th. X, x4, x, x cubed, x squared, x. Now, you probably wouldn't need to prime factorize because you should know that x to the 5th is the same as x times x times x times x times x. There's 5 of them. This is square root, so I look for groups of 2. There's a group of 2, that's going to give me an x on the outside. There's a group of 2, that's going to give me an x on the outside. What am I left with? That lonely x, square root x, and I'm going to multiply these together, x squared, square root x. I find it easier to start by using prime factorization with the variables than it is to try and figure out what goes where, right? So, or what values you have. There are other shortcuts, but once you get some practice at it, you'll be able to see. A to the 7th. If I did this knowing my perfect squares, I would say, well, that's also the same as a to the 6th times a, which would be a cubed times a cubed times a. There's my group of 2, a cubed, left over, a. Prime factorization, this would be a times a times a times a times a times a times a, the 7 of them. There's a group of 2, there's a group of 2, there's a group of 2. That's going to give me a, square root a, my leftovers, that would be a cubed, square root a, same place. Okay. You could mentally think about it too. Okay. How many, this is square root, how many groups of 2 t's can I take out of 9 of them? I can take out 4 groups. So I could say, well, that's going to be t to the 4th with 1 left over t, not 9, t. I could also say, well, that's also the same as square root of t to the 8 times t. Well, t to the 8 is t to the 4th times t to the 4th times t, not 4. Or t to the 4th square root t. Okay, and then it just gets trickier. Now we got a cube root. Well, how many, we have x to the 5th, there's 5 x's. How many groups of 3 x's can I get out of x to the 5th? Well, I can only get out 1 group, x. What would be left over? 2. I could also say, well, that's the same as x cubed times x squared. Well, x cubed is x times x times x times x squared. Well, there's my group of 3. X comes out. What am I left with? X squared. Of course, that should be a cube root, cube root, cube root. Don't want to forget those. Those would be wrong if we did. Question D. How many groups of 3 can I get out of 7? Well, I can get 2 groups, can't I? So this would technically be x squared. What's left over? 1x. Oops. Put that too close. X squared times cube root x. You could do it by prime factorization. Cube root of 1, 2, 3, 4, 5, 6, 7 x's. We're doing groups of 3. There's a group of 3, x. There's a group of 3, x. What's left over? X, cube root. X times x, x squared, cube root x. And then our last example, example 6. Convert the following entire radicals into mixed radicals in simplest form. Well, this is square root x to the 6th, x or y to the 5th. So I could go x times x times x times x 6 times and y 5 times and pull out pairs, okay, using prime factorization. Or I can say, well, this is square root. How many groups of 2 can I get out of 6? I can get 3 equal groups of 2, x cubed. How many groups of 2 can I get out of y to the 5th? Well, I can get 2 groups, y squared. But I have a leftover here, y. Okay. Or if you wanted to see the prime factorization, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Doing square root, there's a group, there's a group, there's a group, there's a group, there's a group. Those all come out. 1, 2, 3, 4, 5. Left with my y. x cubed, y squared, square root y. (18). Now we can mix in numbers. Square root 18, x cubed. So again, this one I would actually do straight to prime factorization. 18 I know is 2 times 3 times 3 times x times x times x. Square root, I'm looking for groups of 2. There's a 3, comes out. There's an x, comes out. What's left over? 2 and an x. And be done. And especially with 32, y7, z8, and 40, x4, y9, I would totally do these by prime factorization. 32, when you prime factorize it, you'll get 2 times 2 times 2 times 2 times 2. You'd have 7 y's. 1, 2, 3, 4, 5, 6, 7, and 8 z's. 1, 2, 3, 4, 5, 6, 7. Looking for groups of 2. There's a 2, there's a 2, so 2 times 2. Left over 2, there's a 2, 2, 2, so there's 3 y's. 1, 2, 3, 2, 2, 2, 3 z's. Oh, I missed a z. 1, 2, 3, 4, 5, 6, 7. There should be 4 z's. 2. Z, 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 Z. What's left over? Well, we had this lonely 2 that was left over, and this lonely y that was left over. This simplifies to 4. This simplifies to y cubed. This simplifies to z to the 4th, square root 2y. And then d as well, except it's cube root. So 40, so somewhere else I would prime factorize 40. 2 and 20, 2 and 10, 2 and 5. So now I know that this is the cube root of 2 times 2 times 2 times 5. 1, 2, 3, 4 x's. 1, 2, 3, 4, 5, 6, 7. Whoops, not writing a 7. 7, 8, 9 y's. 2, 4, 6, 8, 9 y's. It's cube root, so I'm looking for groups of 3. There's a 3. 3. It's not a 3, it's a 2. There's a group of 3 2's. There's a group of 3 x's. There's a group of 3 y's. There's another group of 3 y's and a third group of 3 y's. What am I left over with? My lonely 5, my lonely x, cube root. And simplify. 2x y cubed, cube root of 5x. Done. So your choice, you can figure out the perfect ones that fit, or you can do prime factorization, totally and completely up to you. Check the Scholantis site to figure out what questions are being assigned, and we'll see you next time.